So today we are going to talk about impedance and admittance. And impedance should, for the most part, or at least I hope, be a review of what you guys learned in your Circuits 1 class. So as a recap, way back at the beginning of your circuit analysis careers, you learned something about the relationship between the voltage drop and the current flowing through a linear network. So if we have a linear box network, and it is a two-terminal network, like so, if we apply some voltage, let's call it Vs, and we measure some voltage V test across the terminals of the network, and we also measure a current I test flowing into the network, we defined the resistance of the network as the ratio of V test to I test, which is nothing more than Ohm's law experimentally derived, effectively. So if we do the same thing to an AC network, but now we apply some phasor voltage Vs, and we measure some phasor voltage V test and some phasor current I test, we can define impedance Z as the ratio of phasor voltage V test divided by phasor current I test. Since this is a ratio of two complex numbers, the resultant is also a complex number, and it can be expressed in either a polar form complex number or a rectangular form complex number. So for our polar form representation, we know that our voltage will be of the form Vm angle theta V. Our current will be of the form Im angle theta I. And so we will have a magnitude of Vm over Im and a phase angle of theta V minus theta I, or the magnitude of the impedance angle of the impedance, where the magnitude of the impedance is simply the ratio of the voltage magnitude over the current magnitude, and the angle of the impedance is simply the phase angle of the voltage minus the phase angle of the current. All right. In rectangular form, I'll do this down here. We can express Z as R plus JX, where R is the real part of Z, and it is known as the resistance. X is the imaginary part of Z, and it is known as the reactance. And because we have a rectangular form representation and a polar form representation, we can develop some simple identities for switching back and forth between those two representations, right? So it should be pretty straightforward to understand that the magnitude of our impedance is simply the square root of the real part squared plus the imaginary part squared. The angle of our impedance, theta z, is the inverse tangent of the imaginary part over the real part. And then we can get the real part from the polar form by taking the magnitude and then multiplying it by the cosine of angle z. And we can get the imaginary part by taking the magnitude and multiplying by the sine of angle z. These are literally just cut and pasted versions of switching between polar and rectangular form for generic complex numbers, but using the fact that we have a real part that is r and then an imaginary part that is x. All right, so if we utilize our definition of impedance, ratio of phasor voltage to phasor current, we can determine the impedance of circuit elements, right? So for a resistor, we know that phasor voltage V is equal to phasor current I multiplied by R. We proved that on Wednesday. So if we divide both sides by I, that's going to give us Z, our impedance, is V over I, which will just be R generically. We could express this as R plus J0 in rectangular form, or R angle 0 degrees in polar form. And it should be fairly obvious that the impedance of our resistor here will have units of ohms. For an inductor, we know that phasor voltage V is equal to j omega L times I. And from this, our impedance is generically j omega L. In rectangular form, this looks like 0 plus j omega L. And in polar form, this would be omega L angle positive 90 degrees. And since a Henry is a volt second per ampere, and angular frequency omega is measured in radians, a dimensionless quantity per second, we have volt seconds per ampere multiplied by per second, giving us volts over amps, or also ohms. And another thing we can see here, we talked about it a bit on Wednesday is that for an inductor, there is a 90-degree phase difference between the voltage and the current, which shows up right here, since the angle is always exactly theta V minus theta I, and it will be 90 degrees for this guy. Okay. Finally, for capacitors, our phasor relationship was I is equal to J omega C times our phasor voltage. And so from this, the impedance of a capacitor looks like 1 over J omega C. Actually, let me C over I, 1 over J omega C, generically, which looks like 0 minus J divided by omega C in rectangular form, or 1 over omega C angle negative 90 degrees in polar form. Some of you may be wondering where the negative sign came from, and that's fairly reasonable, okay? I'll do it right up here. J is defined to be square root of negative 1. 1 over J is then 1 over the square root of negative 1. So let's multiply this by square root of negative 1 over the square root of negative 1, giving us square root of negative 1 in the numerator, negative 1 in the denominator, which is simply negative J. So this negative sign here is correct. So from this, well, sorry, let's go ahead and do units as well. So the units of capacitance, the farad, is a amp second per volt. And then we're multiplying that by angular frequency expressed in radians per second. So we have amp second per volt times per second is giving us an amp per volt. And then we take the reciprocal of that, which is a volt per amp, which is again an ohm. So from these relationships, we can see that resistors are purely real, which is why we call the real part of the impedance the resistance. We can see that inductors have a positive reactance. They will always, always, always have a positive reactance. And capacitors, because of this negative sign or this negative angle, will always have a negative reactance. Okay. So this will come into play later on when we're doing things like power factor correction and all that kind of stuff, when we need to minimize or maximize a particular portion of an impedance to get the specified power output. All right. So I hope all of this was review. Anybody have any questions about this stuff? All right. So since impedances all have the same unit of ohms, we can combine them all together just like we combine resistors, which is going to allow us to approach our steady state sinusoidal AC analysis in much the same way that we did our DC analysis back at the beginning of circuits 1. Okay, so impedances combine like resistors. So now let's talk about admittance. Admittance Y is defined as the ratio of the phasor current divided by the phasor voltage, and is therefore simply the reciprocal of impedance. So obviously we're going to have a polar form representation and a rectangular form representation of this complex number. So in polar form, we're going to have Im angle theta I divided by Vm angle theta V, which looks like Im over Vm angle theta I minus theta V, which is simply the magnitude of the admittance with a phase angle of theta Y, where theta Y is theta I minus theta V. Nothing particularly fancy there. It should be fairly obvious that the phase angle of our admittance, theta Y, is nothing more than negative the phase angle of our impedance, theta Z. We can also develop a complex relationship, or excuse me, a rectangular form relationship that is Y is equal to B plus G, can't even read my own writing, G plus JB, where G is the real part of the admittance and is known as the conductance, and B is the imaginary part of the admittance and is known as the susceptance. Okay. Now, I want to be really clear here because this could potentially be confusing. In circuits 1, we define conductance G to be the reciprocal of resistance R. But in a steady state sinusoidal circuit, that is not true because there are other parts that come into play here. So to convert between the two quantities, we can look at the relationship G plus JB is equal to 1 over R plus JX. And what we will find is that conductance G is resistance over resistance squared plus reactance squared, and susceptance B is the negative reactance divided by resistance squared plus reactance squared. And going the other direction, R is conductance over conductance squared plus susceptance squared, and X is negative susceptance divided by conductance squared plus susceptance squared. Trying to think of whether or not I left off a square root of all of these denominators here, which I feel like I very likely did, because the units probably won't seem to work out any other way. So let's, for the sake of argument, go ahead and throw a parentheses to the 1/2 power around all these guys. Using our definitions of admittance, we can easily say that the admittance of a resistor is simply 1 over R. The admittance of the capacitor is 1 over J omega L, or negative J over omega L. Sorry, yes, inductor. Thank you, Ian. And for a capacitor, we'll have omega C. Admittances combine like conductances do in DC circuits, which is effectively the same as capacitors do in a general sense, meaning that if you have two admittances in series, I'm drawing a total blank. Okay. Let's call it Y1 in series with Y2. Y equivalent is Y1, Y2 over Y1 plus Y2. And if we have two admittances in parallel, the equivalent is simply Y1 plus Y2. So they combine in the opposite way that impedances do, which makes sense because they have an inverse relationship with impedance. All right. So this is all of the requisite background work to start doing circuit analysis in the phasor or frequency domain. So my question to you guys is, how much time or review do you want to devote to circuit analysis in the frequency domain before we start moving along to newer concepts like analyzing multi-frequency circuits and things like that? How much of a review do you guys feel that you need for doing this complex math to solve circuits? At least a handful of example problems or something. Okay. Anybody have a problem with that? So let's dedicate the remainder of this class and maybe a little bit of the next class to just working some problems. So let's start by seeing if I have a calculator so I can verify that. Yeah, I do. So let's start with what I hope will be a fairly straightforward circuit. Let's say that we have some source voltage Vs of t, which I will define momentarily. We have a 10 ohm resistor. We have a 0.3 farad capacitor. We have a 5 ohm resistor. And we have a 2 Henry inductor over here. And our ultimate goal here would be to figure out what our inductor current IC of t is, with Vs of t being equal to, let's call it 18 sine 4t plus 12 degrees volts. So hopefully we all recall that we are not going to do this in the time domain literally at all, because it's just a bunch of terrifying and annoying math, completely and utterly useless, because the complex math that we do in the frequency domain turns all of the nasty calculus and trig identities into simple algebra, and therefore that's the ways that we should approach these. So in a problem like this, the absolute first thing that we need to do is to convert this circuit from the time domain to the frequency domain. And we do that by converting all of our voltage and current signals from the time domain into the frequency domain by using a phasor representation of them. And then we convert all of our resistors, capacitors, and inductors into their equivalent impedance. So let's start with our voltage. Sonny, what should the phasor domain or frequency domain representation of this voltage waveform be? Absolutely right. So I'm trying to trip you guys up here by giving you a sine function instead of a cosine function, but we must convert to cosine first in order to get a correct phasor representation. We convert to cosine by subtracting 90 degrees from the phase angle. So that means we should have a magnitude of 18 and an angle of 12 minus 90, which is negative 78 degrees, right? So we'll have 18 negative 78 degrees volts here. Let's take care of both of our resistors. Since the impedance of a resistor is simply the resistor value itself, we don't need to make any changes to them. So our 10 ohm resistor continues to be a 10 ohm resistor. Our 5 ohm resistor continues to be a 5 ohm resistor. I guess technically I should do this first. I'm going to convert my time domain inductor current that I'm looking for into a frequency domain inductor, excuse me, a capacitor current that I'm looking for. So now we need to convert our inductor and capacitor into their frequency domain impedances. We know that ZL, the impedance of an inductor, is J omega L. So that's going to be J times, what's omega in this case, Jared? 4 radians per second. L is 2 henries. That's going to look like J8 ohms. For a capacitor, we're going to have 1 over J omega C. So that's going to be 1 over J times 4 times 0.3. So 1 over 1.2. Negative J 1.25. I might have that incorrect with my mental math. Yep, I definitely do. J5/6 of an ohm. Negative J 5/6 of an ohm, excuse me. Everybody okay with these two values? Anything seem wild, weird, or wacky? Sonny. It's the angular frequency. So it's the number that's the coefficient of time in the sinusoidal representation is always omega. Any other questions? All right, so we have converted our circuit into the frequency domain. So now we have to figure out how we would like to analyze this. I guess I should write down our numbers here. So what kind of circuit analysis could we do here to solve for that phasor current IC? There isn't really a single correct answer. There's multiple ways that we could do this. But I would argue that a circuit of this simplicity should not necessitate the use of nodal analysis or mesh analysis. What?
This looks like an LT price kind of problem.
One of the, so let's talk about that for a moment. You can absolutely use LT Spice to verify your solutions in these for these type of problems. But one of the things that you're going to see, LT Spice by default treats everything as a sine wave. So you're going to have to remember to go through and convert everything to cosines by subtracting 90 degrees and all that kind of good stuff. Another thing that you may have to concern yourself with is that these are steady state sinusoidal circuits, which means we are assuming that this voltage source has been on and outputting 18 sine 4t plus 12 degrees since the beginning of time. Whereas LT Spice says, okay, so it was off and then it turned on. So there's going to be a few transients that need to actually die out and stuff like that.
Is that why it has the time stuff?
That's part of the reason. So what I'm getting at here is you can't actually look at things at like t is equal to 0. You need to look at things a bit into the future, I guess, or as time gets larger and larger and larger, so that all your transients have been sure to die out and you know what's going on. And then it's going to be, okay, so I need to measure my quantities with respect to some reference as well. So you can absolutely check your work using LT Spice, but it's a little bit more difficult in these type of problems than it is for the DC circuit analysis or anything like that. Brandon.
The angle's just confusing you for some reason. Wouldn't you want to shift the sine wave to the left? There is no sine wave. So the left shift is a positive phase angle. Add 90 degrees. I think if you shifted it left, then it would start.
So if you shift a sine function to the left, so let's draw a sine function here real quick. Okay. So sine starts at 0. You may be correct. I may have screwed this up. Here's our max. Here's our min. And this is 90 degrees if this is omega t. Now let's draw a cosine function. So cosine shifted to the right by 90 degrees is sine, which is why it's sine of x is equal to cosine of X minus 90. Right?
But sine would be sine of X plus 90. You start with sine. We went to cosine. Still not seeing it on the line.
I think he's asking like which one is the one you're converting? 'Cause I think I have that.
Right. So I'm trying to think about how to.
Are you starting with sine X and converting into cosine, or are you starting with cosine and converting into sine?
Okay.
Starting with sine and then moving it 90.
But we're not moving it at all. We're representing it as a cosine. So if this is the correct relationship to where a sine function with no phase shift is the exact same thing as a cosine function with a negative 90-degree phase shift, then to represent this as a cosine function, we need to introduce the negative 90-degree phase shift. Is that, okay. No, I understand where the confusion is from, but we're not applying a shift at all. We're not moving this guy to the left or to the right in time. We're saying these two things are functionally identical. To get from this to this includes a negative 90-degree shift. All right. So let's circle back around to my original question from, I feel like 5 minutes ago. How do we analyze this thing?
I'd say do a source transfer. Can you find an equivalent?
Yeah, all right.
So there's lots of different, I've heard literally nothing that's incorrect, okay? So Cheston suggested a source transformation, and then there is determining an equivalent impedance. We could also do Kirchhoff's current law at this node, which would allow us to find the voltage drop over the capacitor directly, and then divide that divide that voltage by the impedance to get the current. All of those are correct, but I think Cheston's suggestion of doing a source transformation here is actually pretty straightforward. Because if we do a source transformation, what we will have is a current source in parallel with a 10 ohm resistor, in parallel with this negative J56 ohm capacitor, in parallel with a total impedance of 5 plus J8 ohms. And then we can easily apply current division to get the answer that we're looking for. That's very, in my opinion, pretty straightforward. It involves 2 steps. Figuring out what this voltage is, or the voltage drop across the negative J56 ohm capacitor, and then applying Ohm's law to get the current is also 2 steps. Talk me through what you're thinking about with regards to finding some sort of equivalent impedance.
After you find the equivalent, you find current going through.
Okay, so you're arguing we could combine these 3, the capacitor, the 5 ohm resistor, and the inductor together into a single equivalent impedance, find the current that's entering that equivalent impedance network, and then use current division. Absolutely, that doesn't seem like it's particularly difficult. Another thing that we could do instead of applying Kirchhoff's current law at this top node is we could use voltage division to get the drop over that equivalent impedance you were just talking about, and then divide that voltage by that negative J56 as well. So off the top of our collective heads, we've come up with at least 4 different methods that would work, and we could always, if we had an abundance of time and a lack of ideas, I guess, we could always find the total equivalent impedance and find the current flowing through the 10 ohm resistor, and then kind of work our way through simple KVL and KCL relationships to finally get what our current IC was as well. So we need to decide on one of the at least 5 different methods that I've described to work this thing. Anybody have any particularly strong feelings about any of the methods? Source transformation, all right. So with a source transformation, we are going to have a current source in parallel with a 10 ohm resistor in parallel with a negative J56 ohm capacitor in parallel with a generic impedance of 5 plus J8 ohms, where all I've done here is combine this resistor and this inductor into a single impedance so that I can very easily see that I have a current source in parallel with 3 impedances, which is why I feel like this particular circuit is ripe for using current division. This is the quantity IC that we're looking for. So the last thing that we need to know is what is the electrically equivalent current source that should be over here on the left-hand side of our circuit? How do we do that?
E over R.
Right. The voltage, 18, angle negative 78 degrees, divided by our resistance of 10 ohms, should give us 1.8 angle negative 78 degrees. I can do that so easily in my head because I know that the impedance of the resistor is purely real. So there should not be a phase shift when I convert to that current. So from here, applying current division, this should be as simple as saying that IC is equal to 1.8 angle negative 78 degrees amps multiplied by 1 over negative J56 of an ohm. Let me write this a little bit better. And then 1 over 10 plus 1 over negative J56 plus 1 over 5 plus J8. So some of you didn't have me for circuits 1, so some of you might not know what the hell that current division thing is. Do I need to explain current division when there are more than 2 elements in parallel? Maybe just a little bit. Okay. So, let me do this down here. All right. So some of you are probably, and we'll do this for just simple resistances first, and then if it works for resistors, it can obviously be applied to impedance as well since they combine in the same way. So some of you may have learned about current division looking at a network like this. That exactly 2 elements in parallel. Let's call this I1. Let's call this I2. And you learned, and let's call this I, the current flowing into the parallel network. You learned that I1 was equal to I multiplied by R2 divided by R1 plus R2, and I2 would have been equal to I times R1 over R1 plus R2. So effectively, the relationship that you learned was the current flowing through resistor 1 is the total current I flowing into the parallel combination of resistors multiplied by the resistor I don't want divided by the sum of the resistors. Okay. There's nothing inherently wrong with this relationship, except that it's only valid for exactly two resistors. A better representation, in my opinion, that works for any number of resistors in parallel So let's call this R1. R2 all the way out to some resistance R sub n. We can call this I1, this I2, and this I sub n. Our current entering our parallel combination will still be just I. I1 would be I, the total current flowing into the network, multiplied by the reciprocal of the resistor we're trying to find the current through, divided by the sum of the reciprocal of all of the currents that are in parallel. Now, we can prove that this is exactly this for exactly two resistors rather trivially, right? I can do it up here because I'm running out of room. So if I have I1 is equal to I times 1 over R1 divided by 1 over R1 plus 1 over R2, that's the same as I times, all right, so we have a factor of 1 over R1 plus 1 over R2, which is just R1 in parallel with R2, right? So that's going to be R1 times R2 over R1 plus R2. And then we still have that factor of 1 over R1 from our numerator. This guy cancels that guy, and we're left with exactly what you're used to. Okay. But this representation, to me, makes more sense for a couple of different reasons. A, it works for any number of resistors in parallel, not just two, so it has a much greater utility. And B, the thing in the numerator is the resistor that we're actually interested in, not the one that we're ignoring, which is odd to me. So I much prefer to use this utilization of current division, even if there's only two resistors in parallel, just because it's easier for me to remember, because it's the one I'm interested in the numerator. So it looks more like the voltage division relationship to me.
And then just the voltage division relationship, except this one, it's the inverse of every element.
Yep, that's exactly right. It is literally the exact same thing as the voltage division relationship, except that it's the reciprocal of the resistors instead of the resistor itself. Jerry. For voltage division, no, so for voltage division, it's the same regardless. It's just the resistor you're interested in divided by the sum of the series resistance. So as a shorthand notation, voltage division looks like the voltage drop over the kth resistor, which is the resistor that I'm saying that I'm interested in, is the total voltage drop over all of the resistors in series multiplied by R sub K, the resistor that I'm interested in, divided by REQ S, the total series resistance. Current division generically is I sub K, the current through the kth resistor, is I, the total current flowing into the parallel resistive network, multiplied by 1 over R sub K. So I'm going to put R sub K down here. And then I have 1 over the sum of the reciprocals of all of the resistors in parallel, which is just the equivalent parallel resistance. Like so. Where Req sub S is just, again, the total series resistance, equivalent series resistance. Req sub P is the equivalent parallel resistance. And it works out to these things look exactly the same if you don't lump it all together. I multiplied by the reciprocals, and for the voltage division relationship, it's V multiplied by not the reciprocals. So we are now in a position here where we can throw this into a calculator and get some answer for I sub C. Sorry. So let's go ahead and do that. 1.8 angle negative 78 multiplied by 1 over negative 5, 6 I, and then too many fractions in my calculator and it was freaking out, sorry. 1 over 10 plus 1 over negative 5, 6 I plus 1 over 5 plus 8 plus 8. I should have just asked Ian. I know we did this 8 minutes ago, I'm sure.
Oh, I also did.
Okay. So I got 0.659 minus J 1.810 amps in rectangular, which is the same as 1.927 angle negative 69.992 degrees amps in Poland. Okay. Yeah. Typically speaking, I would usually, if there's only 3 impedances, I would literally just save them all as variables in my calculator. So I would have called, 1 over or 10 ohms is X, negative J56 is Y, and 5 plus J8 is Z, so that I could just do, 1 over Y divided by 1 over X plus 1 over Y plus 1 over Z, so that I don't have to type in so much stuff and have so many error or potential opportunities for errors. Because I know for TI-36s, in my experience, they suffer from input lag sometimes, whereas if you press too many buttons in a row, it'll kind of skip over some of your inputs. And then I know for the Casios, If the math gets too complex, they just kind of give up and say math error and make you go back and break it down into smaller digestible pieces. So learning how to store and recall variables in your calculators will make your life so much easier for doing all of this complex math.
I think that.
Okay. Yeah. All right. So are we done? No. Because we were asked to find IC of t, which is a time domain representation. How do we convert back into the time domain? Exactly right. So we know from our frequency domain analysis what the magnitude of our time domain analysis result will be. And we know what the phase angle of our time domain analysis will be. So we can just take this. Sorry, this is getting all over the place, but we've had a few tangents here. IC of t will be 1.927 cosine 4t minus 69.992 degrees amps in the time domain. And I leave all of my answers as cosine functions. Just because, I guess. I mean, if you wanted to convert it to sine, you could do so by adding 90 degrees, but I don't really see the point. All right. We have about 13 minutes left of class. Do you want to try to go through another example? Or do you want to, I don't know, ruminate on this while I go try to upload a homework set for you guys? I will get that up. I will get that put up today, I believe. I do need a reminder to actually do it because I'm obviously very forgetful. But yeah, I'll get something up to where you can upload it, because if you email it to me, I'm not going to be pleased. I get enough random emails. Yeah, I mean, it would make more sense for you to get it done sooner rather than later, because the longer you wait, the longer it's been since we talked about op amps and all that kind of good stuff. But as long as you get it in before your final grades are due, I'm pleased. Any other questions? All right, let's knock off a couple of minutes early so that I can go upstairs and literally do the thing that you told me to do.